Structure of benzene. The structure of benzene was a great problem before the scientists in the midst of 18th century. The molecular formula of benzene was found to be C6H6. 6 carbon, 6 hydrogen. For 6 carbon, only 6 hydrogen. That means benzene contains high degree of unsaturation. Benzene is a highly unsaturated compound. But the molecular formula did not match with the molecular formula of alkane, alkene or alkyne. It took several years to find the structure of benzene. Benzene was found to be a stable molecule and it did not undergo, even though it is unsaturated, it did not undergo addition reaction under normal condition. It prefers substitution reaction actually, and the unusual properties of benzene could not be explained by the structure proposed by various scientists, and it was found that benzene, when treated with ozone, we get a triozonide. This suggests that benzene contains 3 carbon-carbon double bonds. A triozonide is obtained from carbon when ozone added to a double bond. Since we get a triozonide, benzene contains 3 carbon-carbon double bond. And also benzene produces only one monosubstituted product, which indicates that all the carbon atoms and all the hydrogen atoms in benzene are equivalent, identical. On the basis of these observations, Friedrich August Kekule in 1865 proposed a structure for benzene. The structure proposed by Kekule was, it contained a hexagon of carbon atom with alternate carbon double bond and single bond. Each carbon atom contained 1 hydrogen. This was the structure proposed by Kekule. Benzene ring contains 3 double bond, alternate position, each carbon with a hydrogen atom. 6 carbon, 6 hydrogen. This is called Kekule structure. So this Kekule structure indicates that there is possibility of 2 dibromobenzene. If you draw the structure of dibromobenzene replacing 2 hydrogen, we have 2 possible structures. One of the structure is this one. Here bromine atoms attached to carbons which are doubly bonded. The second structure is dibromobenzene, where the 2 bromine atoms are attached to carbon which are singly bonded. But in benzene, the dibromobenzene, only one dibromobenzene we obtain. Means only one ortho dibromobenzene is obtained from benzene. So this problem was of a great challenge to Kekule and other scientists. One day Kekule had a dream in his sleep, a snake moving in a circular way. He saw one snake is holding its tail in his mouth and moving this way. From that dream he got the idea of, he proposed that the structure of benzene, this double bond and single bonds are not stationary, they are oscillating. These pi bonds, the pi bonds present in benzene are not stationary, they are moving always, oscillatory in nature. He proposed 2 structures for benzene in which the single and alternate single and double bonds have changed position. Means the position of double bond and single bond have changed. See, single and double bond positions are changed. He proposed that the pi electron, these are the pi bonds, 3 pi bonds, the pi electrons are not stationary, they are continuously moving. Means pi electrons are delocalized. It possesses these two structures are called Kekule structures. Kekule structure of benzene. But the stability of benzene and why benzene do not undergo addition reaction normally and why it prefers substitution reaction rather than addition reaction could not be explained by Kekule structure. Later all these could be well explained on the basis of valence bond theory and the concept of resonance. So let us explain the orbital overlapping concept on the basis of valence bond theory for benzene. According to valence bond theory, we know a bond is formed, a covalent bond is formed by the overlapping of atomic orbital. Linear overlapping of atomic orbital result in sigma covalent bond, but lateral overlapping or sidewise overlapping of the atomic orbital result in pi bond formation. So let us take the formation of benzene with the formula C6H6. Carbon atom in benzene, each of the carbon atom in benzene undergo sp2 hybridization because each carbon atom is double bonded, they undergo sp2 hybridization. Let's write the electronic configuration of carbon. Atomic number 6, electronic configuration 1s2. 1s2 I am not writing. We need only valential electronic configuration 2s2, 2p2. This is the ground state electronic configuration. The excited state, what happened? One of the 2s electron shifted to 2p. So the configuration become 2s1, 2p3. That is 2s with 1 electron, 2p with 3 electron, half filled 2p3. And it undergo sp2 hybridization using 1 s orbital, 2p atomic orbital, sp2. And we can see here carbon contain one unhybridized p atomic orbital. This p atomic orbital half filled do not involve in hybridization. So each carbon atom in benzene undergo sp2 hybridization. Let us draw the orbital picture. There are 6 carbon atoms. Each carbon atom undergo sp2 hybridization and form 3 sp2 hybrid orbitals. Let this be 1 sp2 hybrid orbital. We know sp2 hybrid orbitals orient along the 3 corners of a triangle, trigonal planar geometry. Each of the sp2 hybrid orbitals are half filled, contain unpaired electron. Around each carbon atom there would be 3 sp2 hybrid orbitals like this. Now out of these 3 sp2 hybrid orbitals, this is one sp2 hybrid orbital which would overlap with the sp2 hybrid orbital of adjacent carbon atom. In that process sharing takes place. So this is sp2 overlapping. This result in the formation of carbon-carbon sigma covalent bond. And the other sp2 hybrid orbital also overlap with the sp2 hybrid orbital of the adjacent carbon atom forming carbon-carbon sigma bond. So this is also sp2 overlapping. So for this carbon, there is the 2 sp2 hybrid orbitals are involved in bonding with the adjacent carbons. Now similarly, each carbon atom, so this carbon if you take, it also contains 3 sp2 hybrid orbitals, trigonal planar, half filled. Out of the 3, 2 will be overlapped with the sp2 hybrid orbital of adjacent carbon atom like this. So in that process what happens? Sharing of electrons. So each of the carbon atom uses 2 of the sp2 hybrid orbitals for overlapping with the adjacent carbon atoms. See, each carbon atom uses 2 sp2 hybrid orbitals for overlapping with the adjacent carbon, and each carbon atom now contains a third sp2 hybrid orbital which is half filled. Right? These are the third sp2 hybrid orbital remaining on each carbon, and this third sp2 hybrid orbital would overlap with the 1s atomic orbital of hydrogen atom forming carbon-hydrogen sigma bond. Here also 1s atomic orbital of hydrogen Oneness atomic orbital is also half filled, so sharing takes place. Carbon hydrogen sigma bonds are produced. Oneness orbital of hydrogen. Forming how many carbon hydrogen sigma bond? 6. 6 carbon hydrogen sigma bonds are produced. See, in each of these overlapping, what takes place? Sharing of electron. That means covalent bond formation. What type of covalent bond? All these are linear overlapping, hence result in sigma covalent bond. How many sigma covalent bonds here? Here one sigma covalent bond. This is sigma bond, linear overlapping. Carbon-carbon sigma covalent bond. All these result in carbon-carbon sigma covalent bond. And also carbon hydrogen sigma covalent bond. Here also sigma. So if you draw the structure again, each hybrid orbital on carbon forms sigma covalent bond with the adjacent carbon atom. 2 carbon-carbon sigma bonds. Each carbon make with the other carbon. And now with the third sp2 hybrid orbital, each carbon atom form carbon hydrogen sigma bond by the overlapping of sp2 hybrid orbital of carbon with the oneness atomic orbital of hydrogen atom, forming 6 carbon hydrogen sigma bond. All these are sigma. Carbon-carbon sigma bonds and carbon hydrogen sigma bonds. Due to linear overlapping of half-filled sp2 hybrid orbitals and oneness atomic orbital of hydrogen, forming CH sigma bond. Now, each of the carbon atom in addition to these sp2 hybrid orbital, here you can see each of the carbon atom contain one more p atomic orbital, half filled, which is not involved in hybridization. Unhybridized p atomic orbital is present in each of the carbon atom. So that we can show each carbon atom contain unhybridized p atomic orbital, and this p atomic orbital is perpendicular to the sigma plane. If all these bonds are in one plane, this unhybridized p atomic orbital, let this be the unhybridized p atomic orbital on each carbon, which lie perpendicular to the sigma plane and also parallel to one another. All these 6 unhybridized p atomic orbital, they contain unpaired electron, means half filled. These two because they are perpendicular to the sigma plane and all the 6 are parallel to one another, they can undergo lateral overlapping. And this lateral overlapping takes place in 2 different ways. If you number the carbon atom, like let this be carbon number 1, if this is carbon number 1, let me check another color. This is carbon number 1, carbon number 2, carbon number 3, carbon 4, carbon 5, carbon 6. So these p atomic orbital, unhybridized p atomic orbital can undergo lateral overlapping. So if you consider the 1-2 overlapping, 1 and 2 p atomic orbital overlap one another. This result in the formation of carbon-carbon pi bond. 1 and 2 carbon atom, in addition to the sigma bond, this is carbon 1, this is carbon 2, in addition to this sigma bond, due to this lateral overlapping, one pi bond is also produced, right? Now 1-2 carbon overlapping, then similarly 3-4, if carbon 3 and carbon 4 overlap like this, and if carbon number 5 and carbon number 6 if overlap one another, we get a structure. This is C3 carbon. C3 and C4, there is single bond and double bond. Then this is C3, C4, then the 5th carbon atom and 6th carbon atom also doubly bonded. The double bond is due to the pi bond formation. Pi bond formation due to lateral overlapping of unhybridized half-filled p atomic orbitals on each carbon. So this structure contains, each carbon atom contains hydrogens also. So in this structure, the double bond is formed between C1, C2, C3, C4 and C5, C6 due to the overlapping of p atomic orbital. But there is one more possibility, no? Instead of having this type 1, 2 overlapping, 3, 4 overlapping, 5, 6 overlapping, if the overlapping takes place between, C2 and C3, if C2 and C3 overlap one another this way, what happens? We get double bond, we get another structure in which C2, C3 is doubly bonded. This is C2, this is C3, C2 and C3 are doubly bonded. Similarly, if carbon number 4 and carbon number 5 are laterally overlap, forming a double bond, pi bond between C4 and C5. Carbon number 1 and carbon number 6, if undergo lateral overlapping, there would be a double bond formed between C1 and C6. That means we get another structure of benzene in which the position of the pi bond will be different. Right? Here C2, C3 are doubly bonded. Then C4, C5, C6. This is C1. C4, C5 are doubly bonded. And C1 and C6 are doubly bonded. Both these structures are equivalent. Only the position of the double bonds or pi bonds different. Each carbon atom contains hydrogen, CH sigma bond on each carbon. So there are two possibilities. Means these pi electrons, pi bonds are oscillating in nature. These pi bonds are not stationary. They are continuously moving. We use the term delocalization. The pi electron, how many pi electrons here? These are the pi bonds. The pi bonds, how many pi bonds? 3 pi bonds, right? Each pi bond contains 2 electrons. So 2 pi electrons here, here 2 pi electrons, here 2 pi electrons. Total 6 pi electrons are present in benzene. These 6 pi electrons are not localized between any two carbon. It is delocalized throughout the 6 carbon atom in benzene. In benzene ring contains a hexagon of carbon-carbon single bond and it contains 6 pi electrons. These 6 pi electrons are oscillating or moving continuously over the 6 carbon atom. Or you can see a pi electron cloud above and below this sigma plane. Above the carbon-carbon sigma bonded plane, hexagonal plane, there would be a pi bond, and below which also there would be a pi cloud. Or you can say this pi electrons delocalize over the 6 carbon atom. Their positions are not stationary. They are not localized. They are delocalized. Due to this delocalization of pi electron, each carbon-carbon bond in benzene possess single bond character and double bond character. Single bond character is shown by normal line. Double bond character is shown by drawing dotted line. That means these two structures are in resonance with each other. Benzene can be represented by drawing a hexagon with a circle inside or a dotted circle inside. Since although it contains 3 double bond means 3 pi bonds. These pi electrons are different from the ordinary pi bond present in alkene and alkyne. Because in alkene and alkyne the pi electrons are localized. But here there is delocalization. They are delocalized over the 6 carbon atom. So benzene do not undergo normal addition reaction like alkene and alkyne. So this concept of resonance and orbital overlapping explain the unusual behavior of benzene. Benzene do not undergo addition reaction normally, although it contains a double bond. Because the double bond, the pi electrons in benzene are special. They are involved in resonance or they are involved in delocalization. So they are not readily available between any 2 carbon atom at all time. They are continuously moving over the carbon. So they do not undergo addition reaction normally.